The Sleuth Kit is a set of command line tools that help you analyze disk images for volume and file system data. The tools are developed by Brian Carrier, author of the must-have book for all forensic examiners, File System Forensic Analysis. The Sleuth Kit is used with Autopsy and many other popular forensic tools. In this video, we will walk through using the tools to find evidence and why you should use them in your forensic analysis. The current version of the Sleuth Kit as of this video is version 4.12.1, and you can download it via the link in the description below. If you don't want to download and compile the binaries yourself, you can use the Kane Forensic Distro or Parrot OS, which both have the Sleuth Kit already included. What I'm working with today are 4 images. One is in the RAW or DD format named Mantooth. The second one is an E01 file that is in multiple segments to show you that the tools know how to deal with multi-segmented image files. And if you're using a multiple segmented file, you just need to specify the first segment and the tools will know how to read the rest of the segments automatically. I also have a VHD file and also a VMDK file, just so that we have a little bit of everything. Let's start at the top level and look at what types of image files these Sleuth Kit tools can work with. The first tool is named img_stat, and as the name implies, it will tell you the stats for an image. In particular, it can tell you about the type of the image, the size of the image, and the sector size, etc. In order to see what types of image files mmstat can parse, we can use the -i list option. So I'm going to type img_stat-i list. So we can see that the supported image files include RAW, AFF, the expert witness format, or better known as E01s, and then also virtual machine files like VMDK, and then the Microsoft Virtual Hard Drive format, VHD. So let's take a look at the first image we have, the one that's called Mantooth. So I'm going to do mmstat mantooth.raw. And we can see that the image is in the RAW format. The size is 128 megabytes with a sector size of 512 bytes. So good info to know. And let's go ahead and do the same thing with the VMDK and VHD files. I'm going to do mmstat C drive VMDK, and then mmstat disk file.vhd. Right, and again we get the similar information of the image type, the file size, and also the sector size. And lastly, let's take a look at our multi-segmented image called image2. If I just type the name of the E01, it will give us a stat of the overall image, right? We don't need to specify all the segments. So I'm just going to do mmstat image2.e01. And if I do mmstat image2.e0 ? To bring in all the other segments, I basically get the same thing. So there's really no need to specify all the segments. Next, let's dive into the volume level of the image file. Essentially, this is the partition table of the disk image. So the first tool we are going to look at is called mmls, which gets you the partition information of that image file. So I'm going to do mmls of mantooth.raw. And what we get back is the partitioning scheme. In this case, it's the DOS. And there's no offset to the partition table. And we see that the partition table is in the first sector, right? The master boot record. And the second section is unallocated space here. The first real partition for data starts really at sector offset 63. And it is a NTFS or exFAT partition. Doesn't really know the difference. They're both type 7. And its size is 224847 sectors. Okay, everything here is in sectors. And then we have a second data partition that starts at sector offset 224910. And it is listed as a DOS FAT12 partition with the size of 16,065 sectors. And then we can see here that the remaining 9,904 sectors of the disk is unallocated. So this information is important to note as you want to make sure that you have all the partitions present and accounted for, and there's no significant unallocated space where a partition could have been and then deleted by someone who knows what they're doing. So let's take a look at that image. I'm going to do mmls of image2.e01. Again, note that we just need to give it the name of the first segment, and the tool knows what to do to gather up the rest of the segments. Let's take a look at the vmdk file. So mmls of c drive cl2.vmdk, and it's pretty much the similar thing. We get a partition table with a breakdown of partitions. So now let's take a look at the vhd file. So I'm going to do mmls of newdisk.vhdx. And this one's going to be a little different, as the partitioning scheme is going to be GPT, or GUID partition table, and not DOS. And I did this on purpose just so that we see something different. And because it's using the GPT scheme, we see the protective MBR in sector 0, right? So that's all good. And then the GPT header in sector 1, followed by the entries going through sector 33. The real partitions of a Microsoft Reserve partition starting at sector 34, and then the basic data partition starting at sector 32768. The next command at this volume level is the mmcat, which will output the contents of a specified partition to standard out. So if we want to write out just a partition of a disk image to another file, you can do that by doing mmls and then image2.e01, right, to take a look at all the partitions. And then now let's say we want number 2 here, so we can do mmcat image2.e01, and then the number 2 for partition 2, and then I'm going to redirect the output into a file called image2-p2.dd. So note the partition number specified on the command line is the numbering system that mmls uses, not what you normally consider as the partition number, right? Because normally we would think that, oh, this is the first usable partition, so it's partition 1, but according to mmls, it's actually partition number 2. All right, so let's go ahead and write out the third partition as well into a file, because I'm going to use it later. So I'm going to do mmcat image2.e01 3 for the third partition, and then redirect into image2-p3.dd. So when that's done, it might take a little while because that's actually a pretty big file. We can take a look at the results by doing ls-l of star.dd, and we can see that these two files have pretty full content, and the third partition is significantly larger than the second one. All right, the next command is fsstat, or file system stat, and is used to obtain the details associated with the file system of interest. And the output, we're going to get information like inodes and used blocks and clusters and all that file system related information. For this command, you can basically point to an entire image file by using the -O for sector offset, or you can point it basically to an extracted file system file, which is what we had done earlier with the mmcat. So let's go ahead and do an mmls on mantooth.raw again to see what we have. We see that the first partition starts at offset 63. So I'm going to do fsstat-o 63 mantooth.raw, and then I'm going to pipe it through less because there's actually a lot of information that's going to come through. All right, so the first thing we're going to see is that it's going to tell us this file system here that we're looking at is NTFS, and then it's going to tell us the volume serial number, the name of the volume if it exists, the version of Windows that it's associated with, and because it is an NTFS volume, we see information about the MFT, the clusters, and other NTFS specific information. All right, let's take a look at the partition that we wrote out earlier so we don't have to look at the entire image and count the offsets. So we can do fsstat of image2-p2.dd and then pipe it to less. So remember the dd file is what we extracted out with mmcat in the last section, and it only captures the second partition of the image file. All right, in this case, we have an ext4 volume. So what we're going to get for the rest of this output is ext4 related data, such as the volume ID, the last written to timestamp, the last mounted timestamp and the location of where it's mounted, and then again, information about the inodes and groups and so forth. So definitely tons of good information if you need it for your analysis. Now let's take a look at the other volume that we extracted with mmcat earlier. That's going to be the third partition. So I'm going to do fsstat image2-p3.dd. And this time we're going to get an error that says cannot determine file system type. Let's take a look at the partition table again. So I'm going to do mmls image2.e01. So we see that the description for partition 3 is that it's a Linux logical volume manager, right, of type hex 8 echo, and not just a regular Linux partition, which is usually type 8.3. And I'm using the Sleuth Kit version 4.11, which actually does not support LVMs. You can upgrade to the Sleuth Kit version 4.12, where LVM support is added. Or otherwise, you can manually activate the LVM yourself. And if you want to understand more about LVMs, you can see a full tutorial on LVMs here. But since I am running on 4.11, I'm just going to quickly get the LVM set up so we can actually continue on with this analysis. The first step is to see what physical volumes there are. So I'm going to do sudo of pvs, the physical volume scan. And I actually do see that there are volumes here. The system does recognize. So now the next level is that I want to see what volume groups are there. So I'm going to do sudo of vg scan. And I do see there's a volume group named vg underscore passed over. So I'm going to go ahead and activate it. I'm going to do sudo vg change -a y vg underscore passed d over. All right, and I'm going to confirm that the volume group is indeed activated by redoing the vg scan again. And everything actually looks great. It does tell us that the volume group is activated. So let's take a look at the logical volume groups that are now in play. So I'm going to do sudo lv scan. And so we see the lv underscore swap and lv underscore root. So let's go ahead and run the fsstat on that volume named lv root now. So I'm going to do sudo fsstat /dev/vg underscore passed over /lv underscore root. And again, I'm going to pipe it through less. And here we definitely do see it is another ext volume with all this information. We can definitely see LVMs even though we're not running the latest and greatest of the Sleuth Kit. The next command in the file system level is fls, which gives a file listing of the file system it is pointing at. Again, we can use the -o option to specify an offset into an image file, or else we can have the command point to an extracted partition. So I'm going to go ahead and do the same one as we did before. I'm going to do fls-o63 mantooth.raw and then pipe that to more. All right, so here we see a file listing of all the files at the top level of that file system. For each line, the first column shows you the file type in two structures. The first one is saved in the file's file name structure, and then the second one is saved in the file's metadata structure. If a file is allocated, then both letters should be the same. For a deleted file, they could be different if one of the structures was reallocated to a different file type. So a letter R means a regular file, a D is a directory, and a dash means unknown. So it's more than likely a deleted file. The other letters are similar to the ls-l output, where C is the character device, B is a block device, L is a symbolic link, and so forth. When you see a capital V though, it is a virtual file or directory that is created by the Sleuth Kit for its own usage. So don't confuse that with a file or folder that actually is there. All right, the second column is the inode number. If you see a dash followed by another set of numbers, then you're looking at the metadata address of a NTFS volume. We see here that the 128-1 is a common one because that is the $data attribute. The other common one is 144 something, which is part of the index underscore root attribute. And the third column is going to be the file name. In this case, we're only looking at the root directory. So if we wanted to see the contents of the subdirectories below, we can specify the -r option for recursive. So I'm just going to up arrow and then add the -r and then hit enter. And now we see that there are some extra plus symbols in the far left-hand side before the file type column. So this indicates the number of levels down that the file is in. So if you see one plus sign, then that means it's down one level. And if you see two plus signs, then the file is 2 levels down, etc. And if you see a star between the file type and the meta address, that indicates that the file is unallocated space. So I can go ahead and up arrow and change the more into a grep of \* So I'm going to escape the asterisk there so we can actually grep for it. So in this example, we see that the folder named more secret stuff has been deleted, right, because the types don't match. Right? One is unallocated, the other one says is the directory, and then we also have the star. Note that the metadata number for the folder is 1663-144-7. So we can actually try to see if we can look inside that folder by using the fls command. So I'm going to do fls-o63 mantooth.raw and then the 1663-144-7. So what we do get back is these 3 files which are inside. Alright, so let's take a look at an example of what FLS looks like when run against a ext file system. I'm going to run it on the LVM that we had looked at earlier. So sudo fls of /dev/vg _ passed over /lv _ root. And I'm going to pipe it to less. Okay, so notice the second column is a single digit without the dashes. Right, that was in the NTFS file system. So in ext, we just get a number, which is the inode number. And we see here the files. It looks like a pretty typical listing of a root of the Linux file system. All right, now that we're done with using the LVM, we're going to go ahead and clean up. So I'm going to do sudo vg change -a n vg _ passed over. And then to verify that we have deactivated the vg group, we can do sudo lv scan. And we see here that indeed the 2 logical volumes are inactive. All right, now that we got the basics out of the way, let's take a look at a typical application which uses these tools. And that's the generation of a timeline. So a timeline could be very useful when looking at a compromised device for a criminal case or a cybersecurity incident. This is one of the tools that is used to help explain how an incident unfolded by looking at the changes in the system. For NTFS or exfat, the MFT is the one file that holds all of the information about all the files. And in Linux file systems like ext, there is no such file, so we actually have to create one. So if you have the file system mounted, you can use find along with the stat command to obtain all of the necessary information, such as file permissions and the MAC timestamps and ownership, file sizes, and full path, and all that kind of stuff. And the output of these tools is called a body file, and it gives similar information as that of the Windows $MFT file. So I'm going to go ahead and run the fls command to create a body file from this file system. I will use the -r option to recursively display directories, and I will also use the -m option to output in the time machine format, and then the string after the -m option is what's prepended to the file path. So in this case, I'm going to use the leading slash. So fls -r-m / image2-p2.dd. And I'm going to redirect that into image2-p2.bf. All right, that's pretty fast. So let's take a look at the results. I'm going to do a more of image2-p2.bf. And we see that the file has 1 line per file and each field is separated by the pipe symbol. And it's going to contain a MD5 hash in the first column, if there is one, but in this case it's all 0 since we did not calculate it. It's going to have the full path in the second field, then the inode number, the file type and file permissions, then the UID, the GID, the file size, and then the A time, M time, C time, and CR time. All right, now that we understand what a body file looks like, let's skip that step and go directly to the mactime tool, which will generate a timeline file. So I'm going to do fls-r-m/image2-p2.dd, pipe that into the mactime program, and there's a -b option to specify the body file. And in this case, since we're reading in from the pipe, we're going to use a dash symbol to represent reading from the pipe, and redirect that output to image2-p2.timeline. All right, and now we're going to go ahead and do more of image2-p2.timeline. And we can see it's going to be sorted by time here in this first column. So at this particular time, these files were touched in some manner. And we can kind of step through all the way to the most recent time. Another common function for forensics is to extract files of interest from the image. And we're going to explore a few tools that operate in the metadata layer. That is, they deal with the inodes for the Linux file system, and then the FAT or MFT in the Windows file systems. We can use the command ifind, which will return the inode for the given file if you use the -n option, or the data unit if you use the -d option, or the par_inode for the -p option. And I'm going to go ahead and look for the pagefile.sys file, which is in most Windows file systems. So I'm going to do ifind -o63 mantooth.raw -n pagefile.sys, and it returns 159. Now I can use the icat command to extract the file at that inode number, right? So I'm going to do icat -o63 mantooth.raw 1519, which is what we had earlier, and then redirect the output to pagefile.sys. And when it's done, we can verify it by doing ls-l of pagefile.sys, and we definitely see it's a large enough file to be a page file. All right, so now let's take a look at recovering deleted files. And in order to recover deleted files, we need to know what files are deleted. And we can use the ILS command, which defaults to only listing deleted files. So I'm going to do ILS-o63 mantooth.raw. And so we see here, it's going to list out all of the deleted files on that volume. And in order to recover a file, we can specify that inode number with icat again. All right, so let's just pick a file here. This one, 1723, looks good. So I'm going to do icat-o63 mantooth.raw of 1723. And I'm going to redirect that out to 1723.xxx, since I don't really know what kind of file it is. Once it's extracted, I can use the file command and point it at 1723.xxx, and it's going to tell us that it's a JPEG file. All right, well, if it's a JPEG file, we can actually take a look at it. So I'm going to do mime open 1723.xxx, and here we see the results of that JPEG file. So we just extracted a deleted file. All right, so this is fine. Like, this process is fine for understanding how the tools work. But if we want to recover all of the deleted files, there's a better method. And that's with using the tsk_recover command. So first, I'm going to create a folder where the recovered files will go. I'm going to do mkdir recovered. And then using the sector offset again, point the tool tsk_recover to the file system of interest. So I'm going to do tsk_recover -o63 mantooth.raw. And then lastly, I'm going to tell it where to go, right? The folder that I just made called recovered. And when I hit enter, it's going to go ahead and do all the extractions of those deleted files. And then to verify, we can do ls-R, right, for recursive on recovered. And here we see that all of the recovered files keep their file structure, which is kind of nice. We looked at two common applications where the Sleuth Kit can be used very effectively. The first is to create a timeline for analysis, and the second one is to extract active or deleted files from the image. Notice in this video that we never mounted any of the file systems. Everything that we did was operate on from the image level. We looked at tools that operate at the image level, like img_stat. We looked at tools that operate at the volume level, such as mmls and mmcat. And then we looked at tools that operate at the file system level, such as fsstat, fls, ifind, icat, and ils. There are definitely automated tools that do all this, but it's always good to understand the core of what the tools are doing. Sometimes you may not have the fancy tools available to do what you need, but I always have my Kane distro with me, so I will always have the Sleuth Kit. And sometimes you just need to do something quick, like extracting one file, and you don't want to wait for the image to be processed in one of those full forensics suites. So this just gives you more tools in your tool belt. I know that you will enjoy another Linux forensic video like this one here. Click on the blue monkey to subscribe now. I'm not bossy, I just know what you should be doing. Thanks for your time and happy hunting.